Hello, is my voice clear? Yes, is okay. Okay, thanks. Yeah, just if if it is unclear, just let me know in between. Okay, if something because I no suddenly the connection is not so good. I'll yeah. Okay, so let's get started. I'll start with the following question, which yeah, this question, which was is 1 plus 100 plus 100 square by 2 factorial 100 cubed by also I'm writing if it's not coming then you can okay. Yes, yeah, sorry, I forgot to share it. Yeah, now it should be. Now is it there? Yeah, does the whiteboard appear now? Hello, sorry, hello, yes, thanks. Okay, okay, right. So here once again this is a question about adding infinitely many numbers. And the question that we are asking is that is this finite? Is this thing going to be finite? Okay. Now, and we will try to do this in an elementary way. And let me tell you right away, this was a question which was there in the mock. Okay. But first of all, we just want to understand if this is finite. Let me first explain what the question means from the perspective which we'll be looking at in more details in calculus, in proper calculus. But really, when this kind of question is asked, is this finite? In many series we have seen, where we add infinitely many numbers and we ask if it's finite. What we are really asking is there a minute. What we are asking is there some m, okay, such that 1 plus 100 plus 100 square by 2 factorial. Here I should be putting 1 factorial pattern, 100 cube, 3 factorial. So you should pay attention to this concept, what this thing really means. Obviously, intuitively we understand, is it always less than some number m or something like that? But here, it's a little more than that. So try to see, we are asking that, is there some number m such that this quantity is less than equal to m, not this quantity, I should say, such that this quantity. So I'm not answering the question. We are just trying to understand the question and trying to from the perspective of convergence and such. Okay. Is there some number m such that this is less than m for any n? Now, obviously, this is just a rephrasing. It is just a rephrasing of what we say. But here we see an important thing, that is, when you ask the question of an infinite adding infinitely many numbers, so a priori means, formally speaking, adding infinitely many numbers is not defined. That doesn't make sense. So what we are really asking is, do adding these finitely many things, no matter how many of them you add, does it always remain less than or equal to some m? This is one part of it. Okay. Again, to expand this in more details, it means that if if maybe s0, I can say, if s0 is 1, s1 is 1 plus 100, s2 is by 2 factorial, and so on. Sn is, now all this looks very redundant, right? But you see this will start becoming necessary to know it in this formal way, because there is more than just boundedness that we are looking for, and that will become important, especially when we will have series in which there is combination of negative and positive terms, and that's where we will need more definitions. And well, all that accumulated is really what calculus of sequences is about. But in any ways, we want to just arrive at that naturally from this topic of adding infinitely many numbers. We are essentially looking at this sequence, and obviously this sequence goes on, right? Means that there is an Sn plus 1 and so on. So we are looking at this sequence S0, S1, S2, S3, and so on. Look at, this is called a sequence, just a list of numbers. That's what a sequence is. All know that. This is an infinite sequence, okay? And you can understand what these terms are, right? The nth term of the sequence, the 100th term of the sequence, or 200th term of the sequence, the nth term of the sequence is the addition from 1 to n, is the addition of the first n terms. These are also called partial sums because we are partially adding the series. And what we are really asking for is there a m such that, okay, yeah, again, just expanding this again, just is there a m such that Sn is less than equal to m for all n. But do you agree that this is the same thing? This point is the same as this point. Is there any difference? Does everybody see that these two are the same things? Right? Yeah. So we are primarily, means when we take positive numbers and we start adding them, and when we add many of them, and we start with and we ask the question, is this going to be finite? Then it is just this is what it means. Is there a number m such that this remains less than equal to m? And you can translate it in the language of sequences, and you can ask, is this sequence less than equal to m? And these kind of sequences are called, what should they be called? Bounded sequences. That's the first definition of, in calculus we make the definition of bounded sequences. Again, I'm not answering the question. Answering the question is more about tricks and such. We'll try to do that. But before that, we are understanding this. But this is only one part of the story. Okay. The other part is that we are not just interested in an m such that these terms are less, such that these terms of the sequence or any extent of addition is less than equal to m. That's not the only thing we are interested in. We are interested in, is there a m such that Sn is less than equal to m for all m? And now this is very important. And one second, someone is trying to join. And yeah, okay. And given any error, epsilon greater than equal to 0, okay, there is a n for that epsilon, for that error, okay, such that m minus addition up to that many terms, the error is less than epsilon. Okay. Let me say this again in a slightly different way. We are not just interested in some m. We are interested in in some sense, the least m. Okay, we are interested in the least m, or in some sense, the least m doesn't exist because you are adding up many things. I mean, you're adding up infinitely many things, right? So there is no precise answer to this. In some sense, there is no precise answer. In the traditional sense of addition, there is no precise answer to this addition, right? But we are asking for what is the best m, okay? What is the best m? So maybe at this point, I will remove this. So we are looking for the best m, okay? This is called Sn. We are not just looking for some m. We are looking for the best m. Well, this is not precisely speaking correct. We are not looking for the best m. In some sense, we want to show there is a best m without actually finding it. Most of the times, that's what we do. But it's on one level, they're the same things. We are looking for the best m. Now, what does the best m mean? Right? The best m is such that if you add more and more terms, if you have S1 and then you added another term and made S2, then you added um, a third term, or sorry, started with S naught, right? Then we added a third term, then we went and added the fourth term, and so on. When you keep adding these things, this must get closer and closer to that m. We are asking if such a m exists. Okay. Now you can't just take the minimum of the series. What does that even mean? Right. Does that make sense? We are asking for the best m, and that best m would be that m such that as you add more and more terms, yeah, this addition gets closer and closer to m, as close as you want, and then it stays close. Now, what do I mean by as close as you want? That is what is being captured here mathematically. Given any error, okay, given any distance from m, you can add enough terms, you can go far enough so that it is that close to m. The summation is that close to m. Okay. So we are looking for this kind of m, right? Yes. Right. Let's take an example. Let's take a simpler example. So where we actually know the summation. So when we take this series, right, 1, half, half square, half cube, and so on. Okay, let's forget about the 1 for a second. And we add them. We add these things. What do we say? We say that the answer is 1. Now, 1, I mean, these additions are less than equal to 1, right? What does it mean? It means that if you add however many terms, 100 terms, this will be less than m. If you add however many terms, meaning that rather it will be strictly less. But it was not wrong, but this is more precise. However many terms you add, it remains less than 1, right? You agree? This is correct. But what is more true? Given an error, okay, what do I mean? Let me first say without the error. What I'm trying to say is that these things are not just less than 1, but they are going closer and closer to 1. Right? These additions, if you add more and more terms, they are going closer and closer to 1. See, that is what we want, right? We want that number such that my additions go closer and closer to that number if I add more and more things. That's the number which I'm interested in, right? But now, if I say closer and closer, then that doesn't make sense mathematically. I mean, mathematically, formally, that is not correct. That does, it's meaningless formally. So we formalize this by the notion of error. Okay. So these these things, I'm writing it here on the left side, get the idea is that they get closer and closer to m. And now let me say that in the language of error. What does closer and closer mean? If I'm claiming that these things are getting closer and closer to one, if I add more and more terms, if I make that claim, then how would you verify that claim? You would say, okay, if you are saying closer and closer, it's getting closer and closer to one, then I'm giving you an error. Okay, then you give me an error. Let's say, so I claim, so let's say that I claim that this Sn is, again, I'm writing the same thing here, but in a more concrete context here, okay, is getting closer and closer. Well, to be more precise, I should say arbitrarily close, but probably that's just a blanket term for, closer and closer to one. Let's say someone makes this claim to you, okay, and here you understand what Sn is, right? Adding these things more and more. If I make this claim or someone makes this claim, how will you test it? You would say, okay, if that's your claim, then what will you do? You give me an epsilon greater than 0. You give me a very small epsilon. You will give me a very small epsilon, right? You will maybe give me an epsilon equal to 1 by 10 to the power 200. You will give me a very small epsilon. You will say, okay, let's see. I'm giving you this epsilon, and if you're claiming that your Sn is getting closer and closer, then you will give me an epsilon and ask, can I give some n such that Sn such that 1 minus Sn is that much close to the error, right? That is the epsilon, right? If I make that claim of closer and closer to one, then what will you do? You say, okay, here is the epsilon. If that is a claim, then here is the epsilon. Give me, show me how you will get that, how you will get this much close to one. 1 by 2 to the power 1 by 10 to the power 200 close to 1. And what does that mean? It basically means 1 minus Sn is this for some n, right? Can you give me an n such that if you add that much, you will get this difference? Yeah. No, it will not become, no. So it must work for any epsilon. For different epsilons, I will have to give you different n's. Is that right? For different epsilons, I have to give you different. For example, if the epsilon is this, then I have to produce a very big n such that the difference is less than this. Yeah. Let me say that in another way, then become more clear. Let's see. So now, see, if you forget about this for a second, if you look at this, right? If you look at this, then if you add, if you only take S1, okay, and you take its difference with from 1, then what is the difference? We can surely say the difference is less than half, right? Because already half is S1 is half. If you add another term and then you take S2 means half plus half square, right? S2 means half plus half square. Now if you take the difference, what will it be less than? Or what will the difference be? Yeah, what is the difference? The difference is this, right? Roughly speaking, it is like this. And you know that this is, um, you know that this difference is less than half, right? Because you can take a half common and you get something like this. So you know that this is less than one, that we have already shown, right? This difference is again less than half. Now, but more interestingly, if you take an S3, then the difference reduces. So maybe try to understand it like this. Then you take like this, then you get this, and this is less than 1 by 4. So you see, 1 is a very unique number here, right? Because taking more and more terms, as I'm taking more and more terms, the difference from 1, it is not just that these SIs or S1, S2, S3, it is not just that these things are less than 1. It is not just that no matter how much I add, it is less than 1. That is certainly true. But what is more true is that this difference is shrinking. Right, this difference is shrinking. If you take 1 minus S4, this difference will be, you can just do it in the same way, it will be less than 1 by 8. Is this okay? Right, and this will keep shrinking. That is what we are looking for. So 1 is like the best thing. 1 is like, where these sums, they touch 1 eventually. Obviously they don't touch in any finite case, and the touch eventually is defined by saying that you can get closer and closer to it. So if you, so now if you give me epsilon equal to this, then what will I do? I'll take a very big n. I will take a very big n, right? I can just take n equal to this only, though this is not a good one. I can take this n equal to this. And then what will the difference be? The difference will be less than, you can do in the same way, 2 to the power this, which is obviously less than 1 by 10 to the power 200. So you see the power of this thing, right? That it is not one epsilon. Any epsilon you give me, any degree of closeness from one you give, I can go enough, I can go far enough in the sequence or in the series, I can add enough terms so that the difference becomes less than that. Okay, so 1 is the number. Roughly speaking, now you do not have to prove these things at this stage because you're just trying to get the idea of it. First of all, limit of sequence has to be said more clearly, that this is like sequence only, but in any case. Okay, so 1 is the number. So to summarize, these things, these additions till 100 terms or 101 terms or n terms, these additions are all less than 1. They are all less than 2 also, right? I could have written 2 also. But will they get closer and closer to 2? No. No, right? The gap will always be at least 1. This thing, if I replace this by 2, will it work? No. This will always be less than 1, 9 by 8. It will always be at least different. This will always be at least 1. So that's not good. Right? I want, that is why I'm saying, if we want the best upper bound. That is the smallest upper bound. We want the smallest upper bound. Okay. And if such a thing exists, then we say that this summation, this thing goes there. Okay, so we want the best thing, we want the smallest one. All right, so is there something that I should explain here? Anyone has questions? Yeah. We first were just first of all, any question? Yes, yeah, something, yeah, that's right, but it will still be less. You're right, that's a good point, but it will be still less than 10 to the power 200, because this is very less, this is too less, right? I could have just taken log of it or something like that. In any case, yeah, but it will still be less than this, right? 10 to the power 200, because it is 2 to the power. Yeah, that's right. Any questions? Anyone has any questions they want to ask? Please say. Till now we were just asking if there is a m which is such that all, no matter how much you add, it is less than m. But now we have made it one step, we have gone one step further, which is actually not any step further in some sense, but in another sense it is so. And we'll say the details, but yeah, we have gone one step further in the following. Now we are looking for the smallest such m, and if you take the smallest such m, then these, if you keep adding more and more terms, then the difference from m, the distance from m, the difference from m becomes smaller and smaller, as small as you please. Okay, right. This must happen. This must happen. This is important. So there are no questions. Okay. Then I suppose it's okay. We will obviously be doing this formally when we do sequence, but I think I would just say that because I've always been saying, finite and so on and so on. Yeah, right. But you see, if if there if if such a m exists, okay, if such a m exists, just satisfying only this. If there is a m such that all these things are less than m, right? Okay, then m plus 1 also works as an upper bound. Is that right? Obviously, if all this, no matter how much you add, they are less than m, then obviously m plus also work, right? Then what we do is we take the collection of all the m's which work, and we take the minimum of that set. Okay, and that minimum, why that minimum exists is a problematic thing. That is a deep thing, and that's where the problem is. Okay, but in this case, if you can just show that, but for now we can assume the following. If you can show that you add finite, if you keep adding more and more terms, and they are always less than some m, yeah, they are always less than some m, then you can take the smallest. For now we can assume that you take the smallest such m, and that will work, that will be the best m. So we don't have to worry about anything here. Okay, that's okay, we can always take it. So that's why in this case it doesn't matter, but next example we'll do that, it will matter. Now let's actually come to the question of how do you show that. So we are just asking for, is there a m such that this is less than that? That's all we are asking for right now. Because if there is some m, you can take the smallest of those m, and that will be the best one. Is that right? That will be the best one. Like there are many m's. There is m plus 1, maybe m minus half also worked. I don't know. You just take the smallest among these. Okay, and just assume for now that it is there, and that will work. Okay, let's come to the question. So this was there in the test, and someone used that e, this is equal to e is this limit. But the question is that, I mean, you have to then some maybe we don't. Point is you have to show that this limit exists, and that's not a trivial thing to do. Whatever, if you're using that language of limits, and this, it's not trivial thing to do. You have to prove that, and so on. So okay, then you have to do, and it's not, yeah. And also in the second step, what was slightly wrong in some sense. In any case, I'll say the details that privately, but yeah. So here we do not want to use e and all those limits, because if to show limits exist, and they are difficult than this question itself. And I explicitly mentioned do not use if something. In any case, how do we show that this is finite? That's all we want to show. Let's come to a concrete question. How do we do this? So can anybody think of an elementary way, just by bounding it, some bounding techniques and so on? Does it remind us of a question that we have done earlier? Yeah. So the proof by e is not correct. That's a circular argument in some sense. Can we do this just by elementary way? So what does it, I mean, it should remind us of this question that we have done. Right? We have shown that this is finite. And again, this is very easy. How did we show? Anyone remembers or can think of how to show that this is finite, where I've just replaced the 100 by 1? Again, the idea was to just compare it with the geometric. That's it, the art of comparing it with the geometric series somehow. Can we do that? Okay. No, so that was easy, right? We did something like this. So if you want to show it is finite, you want to show that it is less than, less than, less than something, right? Term by term. So it's pretty easy. Like you have to do something like this, right? Like for example, 1 by 4 factorial is less than 1 by 2 to the power 4, right? And similarly, 1 by 5 factorial is less than 1 by 2 to the power 5, and so on. And like this, you can finish it. And this you can easily prove this. This is basically saying that n factorial is bigger than 2 to the power n, which you can try to prove. It's not hard at all. Just multiplying term by term, you can compare. Okay, so there are no questions in this, right? So it is that problem only in some similar problem, but I've just replaced the 1 by 100. Right. Okay, by the way, here I can just comment a bit, say a bit more. We know that this is finite, right? We know that this, for example, right? We know that this is finite now, and we know that it is less than 3, right? Because 1 plus 1 is here, and this you can compare with geometric series, and so it is, this is 1, so it will totally will be less than 3, right? You can again just show it by the bounding thing we have shown. But 3 is not the best. 3 is not the best, right? It is less than 3. See, this addition, this means that you add 100 terms or 1,000 terms or million terms, it will remain less than 3. But it will not get closer and closer to 3, in the sense that it will not get very close to 3. I mean, yeah, like if I give you epsilon equal to 1 by 100, 3 minus in this one, if you add, no matter how many terms you add, this will not be less than 1 by 100. This will never happen, because 3 is not, 3 is an estimate. Okay, now that is not maybe easy to prove, but 3 is just the bound we put. It is not the best bound. 3 is not the best bound. So then, if 3 is not the best bound, 3 is not the best bound, but there is a best bound. That is not easy to prove. There is a best bound. We look at all the bounds, 3, maybe if you work harder, you can show 2.9. We should work harder, you can show it less than 2.9. You can show 2.95. Maybe you can show 2.8 also. And then, so there are so many things which are above it. There are so many things which are bigger than this total summation. No matter how many terms you add, it will be less than 2.9, something like that. We take the smallest among them. Now, why that smallest exists, that is not easy to prove. But you assume that there will be some smallest, right? Okay. There is a best bound, and historically we denote it, and use we use the symbol E for it. There is no value of E. E is not a number that has an exact value. E is a symbol that is introduced. E is a symbol that is introduced for the best bound of this. The best bound of this exists. Well, in some sense, to be very precise, it does not exist. And we introduce a new number. We expand our number system. Okay, we expand our number system so that it has a best bound. Essentially, this is a new number. The best bound of this is a new number which we call E, which we just call E. Now, obviously, you can use machine to show that it is 2.73 something, means it's as an approximation and so on. But you can never find its value. It doesn't have a value. It's not a number in the rational sense. Okay, right. But now let's come back to the question. Okay, so this is the flavor of sequences and so infinite limits and so on. Okay, that's the flavor, and obviously we'll be making this concrete later. Now let's come to the tactics. From just a discrete maths question, how does this? How do we now extend this technique to this case where it's 100 square and so on? So 1 is replaced by 100. Okay. So you can think about it, but here is my idea. Okay. The idea is to once again compare it with the geometric series. Let's just pick a term. Okay. Pick a term. Say n equal to 1000. Pick n equal to 1000. So if pick n equal to 1000, then the term will be 100 to the power 1000, right? Divided by 1000 factorial. Okay. Yeah, what I want to do, I want to show that I want to kind of show that this is less than. Now this is it's a trick, okay? But you will see why I'm doing this. I want to show that this is less than something, which is something like a geometric series maybe, or something like that. Okay. Yeah, 1 minute. So let me think. Yes, something like that. Yeah. So what I will do is the following. I will split it into two parts. I will split this into two parts. I will do 100 square to the power 500. No, 1 minute. What I will try to show, what my eventual goal is to show that I want to show that the square of this, I want to show that the square of this is less than 1000 factorial. Okay, let's just give me 1 minute. I'll just change this to 2 for the time being. Okay, and then I will do that for 100 also, or maybe let me not change it. Let's leave it like this, and let me just keep this n. Okay. Yeah, I just keep that to n, and then I will do. So you keep it to n only. Okay, I want to show something like this. I want to show that this. So I'm looking at the nth term, and it is like this. It's a slightly obscure technique, okay, but it's just my technique. I just was trying to do this in an elementary way, and this is what I. You pick a term, say the nth term, and this is what it is. What I want to show is that the square of the numerator, not just the numerator, the square of the numerator is less than n factorial. Okay, What that basically means is that 100 square, which is 10,000, 10,000 to the power n is less than n factorial. For a big n, it is obviously not true for a small n, right? If you pick n equal to 1, is it true? No, obviously not, right? If you pick n equal to 2 also, it's not true, right? Is that right? I want to show that if n becomes big, then this will be true. Okay, let's try to understand how these two things are. This one and this one, how these two things compare. Okay. Firstly, we start with 10,000 and this guy is just 1. Okay, so obviously the 10,000 is winning. Then you multiply a 10,000 and here you multiply by 2, right? And again you multiply by 10,000 and then you multiply by 3. That's what's happening, right? 10,000 cube and 3 factorial. Obviously this guy is still winning, right? And he's just winning, just keep winning. Till when will this happen? You're multiplying by 10,000 on the left side all the time, but on the right side you're multiplying by smaller numbers. But this will not keep happening all the time, right? It will happen till you do this the 10,000th time. Till here though, every stage the left hand side is getting more, up till this point 10,000 times. Beyond this the story starts changing. Okay, beyond this the story starts changing. So till here it was fine. This is 10,000 to the power 10,000 and this is 10,000 factorial. Okay, so obviously this is winning. But then what happens next, right? At the next stage we multiply by 10,000 here, but then we multiply by 10,001 here. And you see, then the story starts changing. And eventually, and means after some point of time, this side will overtake the left side. Is that right? This side will overtake the left side. And that's not hard to, but you have to really prove it. Okay, it's not hard to prove because no, if you don't go, no, you have to go beyond because you want to make this you want to make n factorial bigger, and that will not happen in one day. That will not happen in one more step. You might have to take many steps, right? Because this has become very big compared to this. It will take some time, but it will happen after some time. That is the claim. So it may not happen. It depends. Yeah, it will not happen in one step, right? It will take some time. And to really understand that, it's not very difficult. You can try to think about it in your own way, but really what I'm saying is that you have this thing is very big compared to 10,000 factorial. Right? This is very big than 1. But okay, it is very bigger than 1. But if you keep multiplying things like 10,001 by 10,000, then 10,002 by 10,000, right? Then you will multiply 10,003 by 10,000. This will eventually, because you see these are all bigger than 1, right? And they are getting bigger and bigger. So this will overtake. After some point, I don't know when, this will overtake. Right? And then you can cross multiply and get the answer. Is the idea clear? Yeah. Are there any questions? That yeah. See, I brought this. Yeah, I brought this 10,000 in the denominator to look at that ratio, very big ratio. But then this is what I am doing at each step, right? Multiplying by 10,000 on the left and the 10,001 on the right. That basically means multiplying by this ratio on the right. And then I keep multiplying this. These ratios are increasing ratios. So obviously they will overtake this constant thing after some time, because these are increasing and increasing and all are bigger than one also. So you know that. Okay, so you see this will happen. So this will happen after some point of time. I I will encourage that if you're not very sure about it, try to think about this and write this. Even if you don't, not rigorous, that's not a problem. I suppose some of us who are used to this can do it easily. But the idea is new. I believe this idea is good, and we can all take away. Okay, so now let's come back to the question. Okay, this was obvious anyways. I mean, so the point is that, given any number a, a to the power n will be less than n factorial after some time. After some time, it will not be true initially, but after some time it will be true. Okay, and you can ponder over that. Right, so this is true, and what do I mean? I mean that basically means that this will happen after some n, and that means that 100 factorial by square root of n factorial, once again, is less than 1, right? So what does that is less than 1, right? This means that this is less than square root of n factorial, just multiplying by 1 by square root of n on both the sides. Okay, that's why I took a square. I took a square, right? Because see, if I just show this is less than 1, that's no good, right? Just showing that terms are less than 1 is no good. I have to show that they are less than certain thing. Okay, so I have shown, what I have shown is that after some n, maybe I should not say n, I should say this happens for m, maybe. Okay, for big enough, it may be very big number, I don't know how big you have to be, but you have to, it will happen for big enough m, this will hold. So then what can you do? You can forget about the part which is still m minus 1. Okay, you can simply, because see, it will be, that's a finite thing, right? It's a finite thing. You can forget about that part completely, just ignore it. From the part that is m, this part, okay, this part, 100 to the power m, and so on, right? This is where it gets easy, or rather, this is where we can bound it, and so on, right? And then, from what we know, this will be less than, just I'm writing here, okay, this will be less than 1 by square root of m factorial. This will be less than 1 by square root of m plus 1 factorial, and so on. And just like we showed that this is finite, you can show that this is also finite. I can compare it with the geometric series. I mean, you know that this is less than 1 by 2 to the power m square root of that. And like just the geometric, instead of 2, it will become square root of 2, right? And that also you can show, because we have shown that for any r, it is happening. If r is less than 1, then this is summation is finite. That we showed by rectangle, drawing the triangle, rectangle, a square, and so on, right? So it's a convolution of things, and now try to write it, okay, step by step. And yeah, not each step doesn't have to be rigorous, but at least you should honestly understand that, be honest that you understand it. Yeah. Okay, so are there any questions? Okay, so this is it's a very clean technique, and so on. There is a rather interesting thing that happens with this, which can also be used, but let me not go into that right away, because I wanted to cover a lot more things which I have not even gotten at. So let me go to a different topic, and I'll talk about more properties of this later on. And really, well, if you just call this E, meaning there's the best bound of this is there, and we call that E, and so we define that this is equal to E. Okay, I'm not pretending to know the value of E at all. I'm not saying, and nobody knows this, no value. But then we'll show some very interesting properties about this, that it kind of behaves like like if you square this thing, then these ones get replaced by twos. Very interesting things happen. So we'll talk about all that later on, maybe. Okay. Yeah. Meanwhile, let me try to tie up this thing with this example, which some of you may have even seen, but we'll try to answer this in detail. Now, this is again just an infinite addition. And how do I say this? What it is? What this is formally? Formally speaking, I am first taking a one, then I'm taking the second is this, and then the third step I'm adding a one, and then I am doing this, and so on. It's very important that I first add then subtract. You can't say first add all the ones and then subtract. No. Or first add 100 ones and then subtract 100 ones and then add. No, you cannot change the order. It's not commutative. Addition in infinite numbers is not commutative. We'll see all that. Okay. But this is what we are doing. Okay, the partial sums. So there are two questions here. Question number one is, question one, is it bounded? What do I mean by is it bounded? Is Sn bounded? The answer is obviously yes, right? You can just say 2. 2 is the bound, right? 2. Yeah, 2 is the bound. That's because it's very, very clear, right? No matter, I mean, at each step, you know that Sn is less than or equal to 2. I suppose that's clear, right? It's because as you can see, right? It's either -1, 0, or no, I mean, it's 1. Sorry, it's just 1, right? I mean, 2 works, 1. 2 also works. Yeah. Yeah. But 2 also works. Yeah. No, yes. No. So, yeah. If I write this, and if the reality is this, then this is not wrong, because what this says is just a logical point. Okay, it's not related to this topic. It's a logical point that if someone says Sn is less than or equal to, so there's a or, and the or means that okay, it doesn't have to be equal, it's or. Okay, so this is just a safer. Yeah, of course, the actual question then is, does the equality hold? But you're right, if I'm sure that 2 will never hold, then I should put like this to send more information. But yeah, but in any case, I realize it's 1, so it's bounded, right? just like we saw that just like we saw in the case of uh, positive terms, when all the terms were positive, and we ask the question whether it's bounded or not. For some things we get it's bounded. Here also, in that sense, it is bounded. Okay, but the second question, which is more important, okay, is that does it get closer and closer to 1? And here, let me put another condition. What does this mean? It means that for any, again, I'm just writing the same thing but with an extension, which I didn't mention the last time, just putting one more condition here. For any epsilon greater than 0, that means for any error, okay, for any epsilon greater than 0, there must be n, there must be some n, there must be some n such that, okay, the question is, does it get closer and closer to 1? So there must be some n such that 1 minus Sn, that is, if you add that many terms, then it must be less than epsilon for this n and all the n after. All the and for n plus 1, for this n, and n plus 1, n plus 2, and so on. So this is the challenge. You do not just what we saw the last time, right? You give an epsilon, I give you an n such that the difference is less than epsilon. That's not enough. it must also remain less. So that's what I was saying. It must get closer and closer to 1, but it must remain close to 1 also. Okay, so if the difference becomes less than epsilon, if you can give me such a n, then it mustn't oscillate. It should not oscillate away. It should remain. The gap should again remain less than epsilon for the all the n's that follow. Okay, so what I mean is that 1 minus Sn plus 1 should be less than epsilon, 1 minus Sn plus 2 should be less than epsilon, and so on. That is the added condition. That is the added condition. Let's again go back to that thing and try to understand how this was automatically happening there. This was automatically happening there, so it was not needed to be said, but we can just see it. You see, when we took these terms, okay, and the question was, does it get closer and closer to 1? Let's say you gave me an epsilon of 1 by 100. Then what? Then I can give you, let's say, S100, right? Then if you take S100, obviously, 1 minus S100 is less than 1 by 100. Right. I mean, if you add 100 terms, the gap, the distance is, this difference will be not just less than 1 by 100, but obviously way less. I should just take log base 2, but it will be less than 2 to the power 99. Do you guys agree? Right. The gap will be, so I'm giving an error, and so I am being, I've been, maybe I should say, I have been given an error, and my challenge is to produce an n such that the difference becomes less than that. And I produced an n. But then if I add another term, if I take, I mean, if this is true, obviously this is less than 1 by 100, but then this also implies that 1 minus this is also less than 1 by 100. Like obviously, right? If you just add more terms to S100, the gap will just become lesser. And it will keep happening, right? For all the terms later on also. So the thing is that not just for that, so for that epsilon, for that difference, not just that the S100 becomes that much close to 1, but it also remains that much close if you increase the n. That is important. We do not want our, so things that oscillate, we can't prescribe a value to them. You can't prescribe one value and say, yeah, this series is roughly that eventually. You can take that number and work with it. You can take that value 1 and work with it. We can only say that when this series not just gets close to 1, but remains close to 1 also. Is that right? Then only we can say, yeah, you can just work with the value 1 and you can safely assume that all your measurements will work. Right. So that's the thing. The idea is to put a number to this infinite process, one number which will, one stamp which will work for big enough things, right? And that's why we don't just want for this epsilon to there be 100, there will be a n, but for bigger n also it should work. It should, the gap should not again widen and then collapse, widen, collapse. No, it should, at some point it should, not get farther from farther than 1 by 100 from 1. That is the challenge. That's the part, and that's what I'm writing here. Okay, that for n plus 1, n plus 2, it must remain less than epsilon. But does that happen here? No, that doesn't happen, right? Because if you give me some n, right, if you give me, let's say, n equal to 5, then yes, this gap is equal to 0, which is obviously less than epsilon, right? But then everything gets spoiled when you add a 6, right? This becomes 2, I think, or 1 or something like that. So what will it become? 1. Sorry, hello, sorry, can you say? No, for 5 terms the difference is 0, right? from 1. I'm saying the distance from 1. Yeah, you're right. When you add 6 terms, it is 0. Yeah, that's absolutely correct. S6 is 0, right? And that's where the problem is. So it goes close to 1, right? So for epsilon, any epsilon, you can find S5, and S5 is close to 1, where it's exactly equal to 1. But then S6 spoils it. So this condition of remaining close doesn't happen, and this is essential. Otherwise, you can think, right, why would you have a definition which it gets close and then gets far, gets close, gets far? Then you can't really use that number as a stamp on the sequence or the series, right? So this is a situation. This is a situation where you see all the things are bounded, but it doesn't get close to one fixed thing, right? Because it doesn't get close to one. In fact, doesn't get close to any particular thing, right? Because always it oscillates. It always oscillates by at least one or something like that. Yeah. In any case, that this is just we are getting towards things, and obviously, uh, I had more interesting questions I'll do, and then I'll go formally in the definition limits, but that will not do next class. Also, we'll take some more time and develop this. The next class will be more about techniques rather than these concepts. Okay. Meanwhile, I encourage you guys to try this question quick. Just try it. Okay, later on maybe. Okay. This is slightly challenging. Maybe you can think about it. So this is one question which was there in the test. Right? It was very simple question. Is this finite? And the answer is yes, right? Because I mean, this is less than 10 powers of 10, so something like that. It's less than 1 by 10, and this is less than 1 by 10 square, and so on. And so it's obviously finite. There's no question about that. But these questions have some very interesting meanings. Okay, in the sense that, okay, one simple way to say this is just a series. This is a part of 1 by. This is a part of summation 1 by n is infinite, right? It becomes bigger and bigger than anything. But then we're taking a part of this series, we're only taking those numbers which only have ones, which means these numbers, obviously, right? That's the part of this big series. From this big series, which is infinite, there are many interesting sub-series which one can take and ask questions. Okay. I am taking another sub-series. You take those numbers which don't have a one. Okay, these numbers have only ones. You take those numbers which don't have a one, meaning that you take like this till 1 by 9, then you don't take 1 by 10 and 1 by 11 because they have ones. You don't take 1 by 12, 1 by 13 until 1 by 19 because they have ones. You take 1 by 20, then you don't take 1 by 21, you take 1 by 22, and so on. And you go like this till maybe 1 by 30. And then you don't take 1 by 31, take 1 by 32, and so on. And you see, so this is just not the complement, but it's just omitting ones. It's on the other extreme end of the spectrum. No ones. This is just a question I came up with, in the sense that, I mean, there was a harder version of this which I came up with, but that I'll talk about that later. And interestingly, it works. It's elementary. Okay, it can be done. So yeah, the question is this finite? And this is an interesting question. No, it's not the complement. It's not the complement. That's right. It's not the complement. It is on the other end of the spectrum, in the sense that, right, this is like only once, and this end is no ones. And there are many interesting things in between, which I was just asking questions and I was trying, and it was just fun problems. And I put one of the problems for the senior people's mocks also, because the one version of this is like a little hard maybe. Yeah. But in any case, try this. This is a very interesting question. And also, actually, the real root of this question was, is this rational? Which I don't think we can do right now. I mean, even I don't know the proof. This is some Erdos had proved this. That was really the thing. Okay. But in any case, forget about this. Just for fun. Maybe someday we can. Then I can tell you guys, and we can read it and press. Some of you maybe can present it after some time. But in any case, right now, just think about this. Okay, that's the other end of the spectrum. No ones. Is this finite or not? Okay, and if you find that easy, then ask the question: what if there are at most 10 ones? Okay, and think about that. Yeah. So that's it for today. Next time, I will start with the questions that I've given. Okay, and then we'll look at only techniques, and then maybe after that we'll start from the basic of sequence limits, so that we don't have this complicated thing about additions. Okay, and then you see everything will become comfortable. And yeah, so calculus is